In this video, I'm going to talk about the law of cosines. The law of cosines is the other method that we have for solving triangles that are not right triangles. Now, to begin things off, what I'm actually going to do here is take a look at a general triangle and discuss what we're able to do with the law of sines. Okay, so the law of sines is really neat, and we got to see that using some cross products and taking the sine of some angles that we can solve for the other sides or angles in the triangle, and that's a pretty neat thing. Yet it does have a limitation to it, and that's what I want to discuss here first, because that limitation is going to lead us into how we or why we use the law of cosines. Okay, so here's a general picture of a triangle. Whenever you are doing a solving triangle problem, you're going to be given three pieces of information. If it is a law of sines problem, you're going to get an angle and you're going to get a side that would be across from it. Okay, so I just wrote down a couple of letters here, capital A and lowercase a, but these would actually be values is what I'm saying. You would know what this angle is and you know what that side is. But you're always going to get a pair, because that pair is going to complete one of the sides of your proportion. Okay, and as long as you have that, you're good to do law of sines. Okay, and then we can give you any other thing. If we give you this angle, that means the other side could be the sine of B. And then you could solve for, I'll call it x here, that would just be the side that's across from here. You could solve for that one. Now, if you're given a side length, if you're given little b, you can still answer that problem, because you would have this complete side, you'd have little b, and then you would have, this would be your variable this time. Capital B would be your variable, and you'd be solving for that angle. And once you have that angle, then you would have two. You didn't know the third one from the 180 rule, and you can finish the whole problem. But the key thing to using the law of sines is that you know one complete pair. Okay, so what would it look like if you didn't have a complete pair? Okay, so let's ignore all that for now. If you didn't have a complete pair, but you still had three pieces of information, they can look one of two different ways. Let's see, I guess this would be a little c here. This would be one case where you have three pieces of information. You have an angle, and you have the two sides that are around it. So you've got the included angle to these two sides. And here you don't have a pair. You don't know the angle across from B, you don't know the angle across from C. There's no way to figure out what those are, and of course you don't know the side that's across from A. So if you have this case, two sides and an included angle, you're not stuck to the point that you can't solve a problem. You're just going to end up using the law of cosines to do it. The other case that you can't use the law of sines is if the three pieces of information that you are given are all side lengths. Okay, if you don't know any of the angles, then you can't complete the one side of the proportion. And that's it. There's only two cases. Okay, so you're always, in a problem, you're always looking first to see if you have a pair of an angle and a side that are opposites. And if you got that, go ahead and start using the law of sines. If you got these other two cases where you have all three sides, or if you have two sides and the included angle, then you're going to lean towards using the law of cosines. So this is the law of cosines. This equation right here is the law of cosines. It does look a little bit lengthy. Looks like there's a lot of stuff that's going on in there. The one thing that I want to say from the very beginning is not to be too intimidated by it, because once we do get to the calculations with it, it is pretty straightforward, just like the law of sines. There's only two cases that you'll be looking at using the law of cosines, and the way that you solve those two different methods is always very routine, so you'll get used to it. So I haven't really talked about what the formula has in it. It does have all the side lengths mentioned, which are going to be your lowercase letters here. It also has one angle that's mentioned. This is a case where we don't know any of the angle measurements. We just have the side lengths. So what that means is that in this particular usage of the equation, that capital A is going to end up being our variable. Okay, so we know all the sides, the 5, 12, and the 10. Those will be little a, b, c that we have here, and then this is going to be our unknown in the problem. Okay, now the most important thing that we do at the very beginning is we decide what angle it is that we want to solve for. For here, we are looking to solve for all of them, so we can really choose any of them that we want. Let's just suppose that we're going to be solving for theta, that would be the one that we're looking for. So if we're solving for theta, that tells us that the side across from it, 10, has to be little a. It has to be that one. So that's the decision making at the beginning. If you decide for beta to be your angle here, then that means that your little a is going to be 5. So of course, don't get stuck on the idea that these are all going to be A, B, C's in the pictures. They're whatever they are. They can be any letters. They can be theta, they can be alpha. You can have letters like P, Q, R around it. You can have anything. But the main thing is noticing the connection between the little a and the capital A, because we got to build that association of what's opposite. So let's say that we are solving for theta. That means that that's going to be our capital A, and then little a by default needs to be 10. Okay, so we're going to have 10 squared is equal to. Here's the neat thing about B and C. It doesn't matter which one they are, because they do the exact same thing in the equation. B is going to get squared, C is also going to get squared. They're going to get added together. And even over here, they're both just going to multiply together and multiply with the rest of the stuff. So if you switch where the numbers are for B and C, it doesn't change the outcome to the problem. Okay, so we just make sure that we don't use a 10 because that one's already being used. Okay, so we could have 5 squared plus 12 squared. Well, that's 1 squared. Let's fix that up. 12 squared minus 2 times 5 times 12 cosine. We'll go ahead and put theta in there. Okay, so that's how you would fill this in. So if you have all three sides, you choose an angle that you want to solve for. Make sure that the opposite side is all the way over here. The other two can get dropped into either of the spots. So it could have been 12 squared, 5 squared. It could be a 12 and a 5. You can mix all that up, and it's going to work out fine. All right, now here's one of my favorite things about this actual equation, is that if you have to solve for the angle, you can literally just move down the line and undo piece by piece, and you'll end up with your answer. So these two things are just two items that are being added to the rest of everything we've got there. So to undo that, we're going to subtract them. Okay, now this is how I'm going to make the problem look when I set it up. What I'm going to do is keep a list of me just removing piece by piece as I go down the line. Okay, so from the 10 squared, I'm going to subtract a 5 squared. That'll be gone. I'll then subtract a 12 squared, and that'll be gone. Once these are out, we're left with this big chunk that's here. Now, these items are all being multiplied together, and they're being multiplied by the cosine of the angle. So all of these need to be divided out. Okay, so your next step is going to be to divide out the -2. Okay, so we're going to attach that minus to the 2, treat it as a -2, and we'll divide it out. Once that's divided out, we can then divide out the 5 and then the 12. So we'll divide by 5, we'll divide by 12. That is going to get you all the way down until you get to just cosine theta. And to undo a cosine, you can do an arc cosine to remove that. So this is literally all the work that's going to solve for that one. It goes straight down the line, left to right. You just need to remember what the operations are, how we'll do this. And now we'll go to the calculator and we'll just do this. Now, if you know what these look like squared, just type them in, right? So that's 100. We're going to subtract 25 for the 5 squared, right? And it's not a bad idea just to press enter each time, but you can do the first couple steps together if you want. I'm going to subtract 144. At that point, I'm going to press enter. Okay, so subtracting these back to back is not a big deal. After that point, I'm going to do all of these individual. So I'm going to divide by -2. Make sure that on your calculator you choose the negative symbol, you don't choose the -1. Okay, if you're using a TI calculator, if you type a minus sign, which I'm going to type real quick, if you type a minus sign, that is different than a negative and it won't know what you're actually trying to do. So make sure you divide by -2. All right, so I did that. I'm going to divide by 5. Going to divide by 12. And after this, I should get a decimal number. Okay, so you get some sort of a decimal form number here. We haven't talked about why that is, but in another unit, we'll definitely discuss why that is true. And we're going to do an arc cosine of 0.575. And that means that angle theta is 54.9 degrees. So theta is equal to 54.9 degrees. All right, and that's how you solve for an angle. Now we got to do it 2 more times. You have to do it 2 more times here. Okay, so we're going to choose a different one to be the angle. Let's go with beta. Let's say that we're solving for beta. So if we're solving for beta, that means that your little a in the equation is going to be the 5. Okay, so we're going to have 5 squared is equal to, and then b and c are just the other sides. So you have 10 squared plus 12 squared minus 2 times 10 times 12 cosine beta. So you choose your angle, make sure you figure out what side's across from it. That'll give you that number, and then the other 2 just fill in the rest of the gaps. And then as far as solving, I'll go ahead and just do it all on the calculator. Okay, but I'm just moving down the line here to figure out what it is. So I'd start with 5 squared, which is 25. Going to subtract 10 squared and also subtract 12 squared, so subtract 100. Subtract 144. I get that number. I'm going to divide by -2. Okay, divide by 10 and then divide by 12. Like that, and then again, you can see here right before I do my arc cosine, I'm going to have a number that is less than 1. And I will do an arc cosine of that number. I'll actually just recall the answer this time. And that is it, beta. And if you look at the picture, which might not really be drawn to scale, 54 sounded like a good angle measurement that was here. Beta, beta as 24.1 sounds like a pretty good answer there. And then alpha looks like it should turn out to be an obtuse angle. So you have 2 approaches at how you can get alpha. You can either do the same problem again, which really isn't that hard. You could, by the time you've already done 2 of them, you've already got a rhythm. You could do that, or you could go ahead and add up the 2 angles that you got and subtract 180. Subtract those from 180. Let me go ahead and do that real quick, and then I'll show you quickly the calculations of the other. So I'm going to add up 24.1. All right, is 79, and subtract that from 180. So I'd be expecting that alpha is 101 degrees. Okay, expect that it's 101 degrees. All right, for the math part of it, yeah, I'll go ahead and write it down. So for solving for alpha, it's going to be 12 squared is equal to 5 squared plus 10 squared minus 2 times 5 times 10 cosine alpha. So we'll take 144. We're going to subtract 25, subtract 100, divide by -2, divide by 5, divide by 10, and last we'll do an arc cosine. Notice that we've got a negative number this time, okay, but it's still less than 1 is a negative. We'll do an arc cosine of that answer, and there you are. Rounds up to 101 degrees. Yeah, I guess I'll have to call it that because the 5 is going to round that up to a 10, and then we'll be at 101 degrees. Example number 2 is going to demonstrate the other case where you would be using the law of cosines. For that, you are going to be given an angle, but the angle is included between the 2 known sides. So you've got an included angle of 130 degrees. All right, so I'm going to go ahead and make a sketch for this because I didn't have one. Always a good idea. All right, the angle that I made up here, I wanted to make sure that it was obtuse because that's an obtuse angle of 130 degrees, but it doesn't have to be exact. I've probably only made like 105 degrees. I'm going to guess that's what I did, but nah, it's hardly obtuse at all. Okay, but usually what I'll do is if I have an obtuse angle, I'll try and make that part look a little bit larger. It does not have to be exact. All right, so the two sides that are around it, because it mentioned this is an included angle, the two sides are going to be rounded are 3 and a 7. So that'll be 3 and that'll be 7 since I do that one longer than that. And I'll go ahead and just close this off. Close that off. All right, so this is your other case. You've got an angle, but you don't know the side across from it, which means you can't do the law of sines. We're going to have to use the law of cosines for this one. All right, now remember our template is a squared is equal to b squared plus c squared minus 2bc cosine a. All right, and the letters are just arbitrary. It's just trying to give you the relationship that little a and capital A are two things that are across from each other. Now, like I had mentioned in example 1, we didn't have both of those, right? So it ended up that we were solving for an angle measurement. In this case, we actually do have an angle. We have the 130 degrees. So what you're going to be solving for is going to be the base of the triangle. You're going to have to solve for the side that's across from the given angle. So I'll go ahead and just add an A to the picture in this case. Okay, so you're still looking for that relationship. Even though it's an incomplete relationship, which in law of sines you're looking for a complete one, even though it's an incomplete one here, that's what you want to find because it tells you what you're going to be using for these two. All right, and then the B and the C are the 3 and the 7, whichever one you want being B and C. All right, so we don't know A, so that's going to stay our variable, little a that is. All right, so that's going to stay our variable as a squared. We then have 3 squared plus 7 squared minus 2 times 3 times 7 cosine 130. All right, and now what I want you to do is take a look at this equation, this massive looking equation with all these numbers in there, and really start thinking about what it is that you're trying to solve for, where's the variable, and how difficult it actually is going to be for solving that variable. So the only variable that's in the problem is little a. It's over here. And if you notice, it's, aside from being squared, it's the only thing that's over here on the left. That's it, the only thing that's on the left. Maybe more importantly is that the only things that we have on the right are numbers and operations, which means that all of that stuff can just be evaluated. You don't even have to do it in pieces. You can literally take all of this information, just put it into a calculator and evaluate it. So let's do that, okay? So we're going to do 3 squared plus 7 squared minus 2 times 3 times 7 and cosine 130. Okay, and I'll double check that I typed everything in correct this time. Here you are going to be using the subtraction. In example number 1 where you're dividing, you treat it as a negative. So this is going to be the subtraction symbol in this case. All right, so everything looks good. I'm going to go ahead and just press enter, and I'm going to get that answer, which is about 85. Now, obviously the base is not 85. That'd be insane. This is a 3 and that's a 7. This is not 85. But what the 85 represents is that side squared. So we got one more step, which is to take the square root of that answer. Comes back as 9 point, we'll just call it 9.2. So A is 9.2, and now that number makes perfect sense for the problem that we've got here. Now that we've done some practice problems using the law of cosines, we're going to go back and look at the proof for it. This should be a little bit easier because doing the problems is going to get you used to what all the letters represent. You're going to know that the little letters are the side lengths and that the capital letter is one of the angles, and it would be across from that side length. So now we're a little bit more familiar with the actual equation. This should go a bit better. All right, so the diagram that I got here, it does have lots of stuff in it, but where it all begins is just with a triangle that is not necessarily a right triangle. Okay, you got vertices A, B, and C. Okay, you got A, B, and C. You've got the side lengths across from those labeled as little a. you've got little b, and you've also got little c, which is down here. Okay, and like with the proof for the law of sines, what we're going to do is drop a perpendicular down in the picture. That's going to be here. You're going to drop down a perpendicular. We're going to go ahead and call that h because we'll be using that side length as kind of like an in-between piece as we go through the proof. So we'll call that h, obviously for height. We'll call that h. But when we draw that line, it actually breaks up this side here, which is going to be important to the formula. See, all the sides are user. So it's going to break up c. Okay, it's going to break it at this point. So what we're going to do is introduce one more variable, which is right here, and say that the distance from A to that point, we're calling it d for now, that A to d is going to be x. Okay, and now for the other side, instead of creating a third variable, maybe calling it a y, what we're going to do is say that that one is actually the difference between the full length c and the part that we're calling x. So that way, even though it might look more complicated than a single letter by using a c minus x, it's better because we're not introducing more variables. If we can introduce the least number of variables possible, it's always going to be easier to work with. All right, so when we do that, it's going to break. So when we drop that down, it actually broke it into two right triangles. It broke into two right triangles. And what that's going to allow us to do is to write two different equations that involve the Pythagorean theorem, which are these. So for the triangle on the left, b is the hypotenuse. It's across from that right angle. So we can say that b squared is equal to h squared plus x squared, because h and x are going to be the leg lengths of that right triangle. Now on the right, a is the hypotenuse, so you're going to have a equals. You have the leg length again, which is going to be h, so you got h squared plus. But for this part, you are going to need to write it like this. It's going to be c minus x, all being squared. So you have a binomial that's being squared versus just a single number. What we're going to need to do with that in just a bit is have that expanded out. So I'm going to go ahead and work on that piece. Now you should be able to, by the time that you're in pre-cal, you should be able to just expand that out and just do it. Okay, but what we're going to do is, just to make sure, we're going to go ahead and go through all the steps. All right, so squaring that is the same thing as just multiplying it by itself. Okay, do that. So now we're going to do a bunch of distribution. We're going to do c times c, which gives you c squared. We're going to do c times negative x, which will give you negative cx. You're going to do negative x times c, which is actually the same thing as what we just did, just backwards. So we'll go ahead and write down another minus cx. Last, you got negative x times negative x, which is going to give you a positive x squared. Those negatives cancel. Now these two are like terms, so you can simplify that as negative 2cx. Just drop down the rest. All right, and that's what this looks like expanded out. All right, so what we're going to do, we're going to expand out the second equation. We just did that, sort of. We expanded out this part. So we're going to take the equation, we're going to expand that out, just took care of it. That's this piece, okay? And now what we're going to do, the second part says we're going to substitute b squared in, okay? But to make this work, we're going to take that x squared that we have at the end, and we're going to move it forward a little bit. Not all the way to the front, but we're going to move it right here, right between the h squared and the c squared, which you'll now see in the third line. And the reason that we do that, we move it there, is because h squared plus x squared is right up here, which is b squared. So those two terms can actually get substituted for, or substituted in with, b squared. All right, so now our second equation has, with some substitution and expansion, has become this. And if you look close at it, you're going to start to actually see the law of cosines appearing. You've got the a squared is equal to b squared plus c squared, right? That's up here. A squared is equal to b squared plus c squared. After that would be minus 2 bc cosine a. What we have is minus 2 cx. Okay, so we're missing the b and the cosine a. We're missing those two pieces, but we do have an x that's in there. All right, so the last part of this, we go back up to the picture and we think about what we have an x that's in the equation, but what we want to have, so we've got an x over here, but what we want to have is a b and a cosine a. B and a cosine a. So if I take a look at the triangle that's on the left, that sort of involves all the things that I'm talking about. It's got the x that we don't want, it's got the b, and it's got the capital A that we want. All right, so what I'm going to do is set up a trig ratio that involves those things here. Now, x is the adjacent to a, b is the hypotenuse, so adjacent over hypotenuse is cosine. I could say that the cosine of capital A is equal to x over b. That's what I have down here. The cosine of a is equal to x over b. Now, real quickly, you can solve for x. You've already done enough of these problems. You just multiply the b over, which is going to give you b cosine a is equal to x. And if you take that, here, I'll box it there. If you take that and substitute it in right there for x, because it is equal to x, you get the law of cosines. So you've got your a squared equals b squared plus c squared, still all there, minus 2. You've got your c value, and now we're putting in a b cosine a. The only thing that is different about this versus how we normally write the law of cosines is that these two letters are backwards. But that doesn't make a difference. That's called the commutative property. You can multiply in any order and it's fine. So what we would do is just flip-flop those, and now it matches perfectly.
Later, blah.